Also, I should point out that, again, as I said in the announcement, I'm combining exam 2 and 3 together. So we're only going to have 3 exams and the final. I was asked if there's a exact schedule for when those exams will be. I don't have one. I know that the final exam will be from that Wednesday till that Friday at midnight. So you'll have 2 days and 3 hours to get through it all. It will cover everything. Having said that, I have not decided yet if the last day of class will be a review day or if we're going to go into other material. Based on what the schedule looks like, we're actually probably about a day ahead of what a normal semester would be. So we may have a review day, we may not. I don't know yet. Having said that, let's get into this. If I click on the right button, there we go. All right. So we've been talking about exponential functions. A natural question might occur. What if we want to undo the exponential function? So instead of saying f of x is equal to b of x, let's say we want f inverse, so that if we put y through it, we're going to get out x. What would that inverse function be? That's the question here, right? And the answer to it is that it's going to be what's called a logarithm. So the log base b of x is equal to y if and only if x is equal to b of y. So what exactly does this mean? This means that given whatever your base is, x is going to be what you get out when you raise that base to y. So log base b of x answers the question, what does your exponential have to be in order for you to get x out of this? Make sense? Now, having said that, there's some notation that we need to take into account. If our base is equal to 10, we usually just write log of x. And if our base is e, we just write the ln of x. So for the rest of the numbers, let's say log base 2 of y is equal to x. Well, that answers the question of what power you have to raise 2 to get y. Keeping with the notation before, we would swap those variables, but the idea holds, right? So having said that, knowing what we know about functions and inverse functions, what do you think the graph of a logarithm would look like? Well, I've said before, we've seen before, that if we have a function actually write it like this. If we have a function f of x, its inverse, for now I'm actually just going to consider the positive part, its inverse would be the reflection across the line x equal to y. So the inverse function would have a graph looking like that, right? Having said that, we know that for a base larger than 1, an exponential function looks something like this. The graph of an exponential function. Let me draw this better. So the graph then of the logarithm, well, it's going to look something like this, if I can get this drawn the right way. Log base b of x is equal to f inverse of x. And wow, I cannot draw this today. There we go. I'm doing it right. It's going to look something like that, right? So having said that, some more definitions. The definition of the natural logarithm is that the ln of x is equal to b if and only if e raised to b is equal to x. So what we're saying is log base e of x is equal to some b if when you raise e to that power of b, you get x back out. And we read the ln as the ln. The natural log is just called the ln in notation. So just some details, some points here. We know the natural log of 1 is equal to 0 because e raised to 0 has to be 1. We know the natural log of e is equal to 1 because e raised to the first power is equal to e. We know the natural log of 1 over e is equal to -1 because e raised to the -1 is equal to 1 over e. So forth and so on, right? Now looking at these, like I said, I did draw that wrong. My bad. I knew I did. These things, I don't know how I managed to do this actually. These things look like this. There's e, the exponential, and there's the logarithm. That's what I was trying to draw before. And that's what we're seeing here in this graph, right? That the function f of x equal to e to the x, that's this gray graph here. And its inverse, well, the inverse function, we know its graph is going to be the same graph, just reflected across the line x equal to y. So we get this graph here. And this is the graph of the inverse function of x equal to the ln of x. And just like with any inverse function, the domain and range flip, the intercept flips, and then we have a couple other properties that follow from that reflection, right? Because our function is continuous, the inverse function is continuous. I should say because it's bijective. Surjective. So what if we wanted to sketch some of these graphs? Well, the ln of x plus 1. Let's stop and think about when you pass through 1. We know that the graph of the ln looks something like this, right? And this point is the point 1, 0. So what this tells us is that the ln of 1 is equal to 0. If that's the case, here, when we pass 0 through, so when we say x is equal to 0, we're still taking the ln of 1, right? So that means this point gets shifted over to 0. Similarly, when we say, for example, in just the ln case, that, draw another point up here. This is the point e, comma 1. When we pass e through, the ln is going to come out to be 1. So if we subtract 1 from e, that's going to be the corresponding x value in our function, in our new function, right? Does that make sense what I mean? So that's going to be, let's say, somewhere over here. Our function, the graph of our function, is going to look something like that. Cool. Now there's something I've left off here. There's an asymptote here. And that's because, let's go back to the original function. The exponential, there's no power that we can pass through. There's no value of x that we can pass through to make this function equal to 0, right? So this would become the original function would be asymptotic with the x-axis. But when we reflect that across the line x equal to y, we get that the inverse function must be asymptotic with the y-axis, or to when x is equal to 0, right? So we have an asymptote here for the inverse function, that's the ln of x. And we have an asymptote here for the original function, that's e to the x. So in our graph that we've got on the board, we actually have this asymptote whenever x is equal to -1. Folks at home, does this make sense?
Yes, sir.
Did that make sense?
Yes.
Let me make sure this is turned up.
Hello.
Let's not turn that up because that's going to cause noise between the two mics. All right, cool. Somebody said yes. So again, like I said, we have that asymptote at -1, at x equal to -1. That makes sense because the ln of 0 doesn't exist, and we're asymptotic to x equal to 0 for just the ln of x. Then this thing can't exist when x is equal to -1, and that must correspond with that same asymptote, right? And also, all of this follows just from the transformations of graphs and functions that we've talked about in algebra. For folks who need a review of that, I do have review notes in Blackboard. Similarly, we have, in this case, we're going to shift over right by 2 units because we're subtracting 2. And then we're going to stretch everything by a magnitude of 2. Stretch everything vertically. So just some properties that happen to occur, because a function composed with its inverse function is still going to be equal to x, and an inverse function composed with a function is going to be equal to x. If we take and compose something like e to the ln of x, well, if f of x is equal to e of x, then the inverse function of f of x is equal to the ln of x. So what this is the composition of these two functions, right? That is this first case here. So we're just going to get x back. And this makes sense because the ln of x is answering the question, what power do you have to raise e to get x back, right? And then you're raising e to that power. So you're going to get x back. And that's why this is happening this way. Similarly, if we were to reverse the order, we'd get the exact same thing. Hence the following properties. So having said that, why don't we all very quickly try to work on A? See what you come up with for that. While you all are doing that, I'm going to do B really quick. So what y'all get for A? Yeah, it's just the square root of 2. And in the case of B, it's just going to be 3x. Now some properties of logarithms, and y'all are definitely going to want to memorize these. You're going to want to know them inside and out, forward and backwards. If you have the ln of two things multiplied together, that is equal to the ln of one thing plus the ln of the other thing. If you have the ln of x raised to a power, that's equal to that power times the ln of x. And then the second property is a result of the other two. So let's see that second property using the first one and the last one. We've got the ln of x divided by y. Well, we can rewrite that as the ln of x times y to the negative first power, which is equal to the ln of x plus the ln of y to that negative first power, which is equal to the ln of x plus negative 1 times the ln of y, or the ln of x minus the ln of y. So here, we're using that first property, and here, we're using that third property. And from here to here, all we're doing is rewriting things in terms of a power, right? So knowing this, how might we rewrite some of these LNs? Now notice we have to make some assumptions. We have to assume that X and Y are greater than 0. And the reason why is because we can't put values in 0 or less, right? Well, the ln of 10 divided by 9, based on that second property, is going to be the ln of 10 minus the ln of 9. B, the ln of the square root of x squared plus 1, that's going to be equal to the ln of the quantity x squared plus 1 raised to the 1/2 power. And by that third property, that's going to be 1/2 the ln of x squared plus 1. Now, can we do anything else to this? Can we reduce that any further? Looking back at our properties, no, not really. The ln of two things added together is just the ln of the two things added together. You're not going to be able to reduce this any further. And we could go on and work out the rest of these problems. Here we're going to get the ln of x plus the ln of y minus the ln of 5. At D, we're going to get the ln, or minus 8, we're going to get 2 times the ln of x plus the ln of x plus 1. And just looking at these really quick, again, property 2, property 3, property 2 and 1 is used for C, and D uses 1 and 3. What if we wanted to go in the reverse direction? We could. So looking really quickly then at B, we've got 2 times the ln of x plus 2 minus 3 times the ln of x. Well, by property 3, this is equal to the ln of the quantity x plus 2 squared minus the ln of x cubed. And by the second property, this is going to be the ln of x plus 2, that quantity squared, divided by x cubed. That's it. So what if we want to start solving things? What if we want to solve for what x value makes this statement true? How are we going to do that? How are we going to solve for x here? Thoughts? Let's start by assuming we have a function f of x is equal to e to the x. This thing is going to be equal to y. Then the inverse function, f inverse of y, that's going to spit out x. And in this case, we know that's going to be the ln of y. So if we apply the inverse function to both sides, we're gonna get x on one side and the solution for it on the other, right? Make sense what I mean? So what I'm saying is, if e to the x is equal to 5, then this tells us that the ln of e to the x is equal to the ln of 5. But hey, this is just going to be x. So we're going to have that x is equal to the ln of 5. So with that in mind, why don't y'all try b really quick? We'll give y'all about 3 minutes to do that. What do y'all think? Did anybody get 10 times the ln of 4?
I got 0.1 t equals ln 4, but I didn't want 0.
Well, you're on the right track. Now we just have to solve for t, right? So we need to isolate t on its own. So we would divide both sides by 0.1, right? Which is the same thing as multiplying by 10. So let's see that really quick. So we've got 10 plus e to the 0.1 times t is equal to 14. Now at this point, I would like to go ahead and turn this into a fraction. It's an easy enough fraction to write. Let's do that. This is 10 plus e raised to the t divided by 10 is equal to 14. This tells us then that subtracting 10 from both sides, e to the t divided by 10 is equal to 4. So taking the ln of both sides, we're going to get t divided by 10 is equal to the ln of 4. Multiplying now both sides by 10, we get that t is equal to 10 times the ln of 4.
So if I was to keep it as a decimal and divide, would the answer be wrong?
No.
So it's like ln 4 divided by 0.1.
No, it would not be wrong. So checking it out really quick, in that first case, our solution was in fact x equal to the ln of 5. And in our second case, we did in fact get that t is equal to, excuse me, 10 times the ln of 4. Okay. What about if we're given the case where they're not exponentials? I mean, yeah, when they're not exponentials, they're logarithms. Then we're just going to exponentiate everything, right? We're going to come over here, the ln of x, raise e to the power of ln of x, and that's going to be equal to e raised to the power of 5. Agreed? Well, that's just going to give us x is equal to e to the 5th power. Everybody cool with this? Now, in the case of b, there's a couple of different ways we could do this. I'm going to show you the long way, and then I'm going to show you the short way. So with b, we've got 3 plus 2 times the ln of x is equal to 7. Well, this tells us then that 2 times the ln of x is equal to 4, because we subtract 3 from both sides. Well, 2 times the ln of x, this is equal to the ln of x squared, which is still equal to 4. Now, exponentiating both sides, we're going to get e raised to the ln of x squared is equal to e raised to the 4th power which is equal to x squared So now we're going to take the square root of both sides, which is going to give us that x is equal to plus or minus 4. Are we done? Folks at home, what do you think? Are we done once we get to this point here?
Yes.
Yep.
I don't think I can hear y'all. All right, try that again.
Yes.
Yeah.
You think we're done here? Not quite, because if we look back at our original equation, we can't put -4 here. So because the ln of -4 does not exist, x has to be equal to 4. Now for the other way to do it. The other way, we're going to come over from this second line. We've got 2 times, my mistake, I miswrote this. It's supposed to be the square root of that, so it's plus or minus e to the second e to the second. Typo on that, I apologize. But we're going to come over, like I said, in this other approach, straight from this second line. And say, all right, cool, we know that 2 times the ln of x is equal to 4. Which tells us then that the ln of x is equal to 2, which tells us then when we exponentiate both sides, e to the ln of x is equal to e to the second, but e to the ln of x, that's just equal to x. So we have x is equal to e to the second. Now, very quickly coming back to this, for the folks at home who aren't sure how I went from x squared is equal to e to the fourth to x is equal to plus or minus e to the second. I took 1/2 power of both sides, right? But we're solving for x, so we could have plus or minus, and that's where the plus or minus comes from. But then when we check, we say, all right, well, the ln of a negative number doesn't exist. So we have to stick with e to the second power. Now, really quickly, just to reiterate, the reason for this is that the domain of e to the x, well, that's any possible number, right? Negative infinity to infinity. But the range of e to the x that's going to be 0 to infinity, but we can't ever reach 0. And since the ln is the inverse function, we're going to flip the range and domain for the ln. The domain of the ln of x is equal to 0 to infinity, and the range of the ln of x is equal to negative infinity to infinity. And again, this is why we have that asymptote at 0, right? And this explains why we have to throw out this negative value. So really quickly checking, for that first problem, we do in fact get x is equal to e to the fifth. And for that second problem, we do in fact get that x is equal to e to the second. Dope, so I'm not telling you anything wrong yet. So when might we use some of this? As an example problem, we've got what we have right here on the screen for y'all. If we have some principal amount that we deposit into an account that's incurring interest annually at a rate of R, and it's compounding continuously, my mistake, whose annual interest rate is R, and it's compounding continuously. We want to know how long it'll take for our balance to double. So what is the question we're asking here? What do y'all think? What's the question here? Well, if we go back, what slide was this on? Slide 40. If we go all the way back, to continuous interest, wherever that problem was, that was on another slide, or I mean in another set of notes. Let me pull those up really quick. Stop share. looking back at previous notes, compounding continuously, we know that the amount in an account is equal to our principal amount times E raised to our annual rate times the time in years. Now coming back to our problem. Coming back to our problem, what we're asking is to solve for whenever we have an amount twice what we initially put in. So that's going to be 2P is equal to P times ERT, right? E raised to the RT, I should say. So to solve this, the first thing we might notice is that we can cancel out these P's, right? So let's go ahead and do that. That's going to give us 2 is equal to E raised to the R times T. Well, we're trying to solve for how long this takes. So we need to solve for T. The only way we can do that is if we take the ln of both sides. Taking the ln, we get the ln of 2 is equal to the ln of E raised to the RT, or just RT, right? So ln of 2 is equal to RT. Now to finish this, we're just going to divide both sides by R. We get that the ln of 2 divided by R is equal to the amount of time it takes to double your principal. Starting to write twice as much. So looking at their solution, they set up the problem the same way, right? They say, all right, we know that the amount in our bank account can be modeled using this equation. This is because we're compounding interest continuously. We don't know what R is, we don't know what our principal amount is, but it doesn't really matter because we just want to know for some given annual interest rate, how long do we have to wait to double the amount? So what is T? So we start off by saying, all right, set A equal to 2P. We can cancel these P's from both sides to get to here. When we do that, we end up at the ln of RT is equal to the ln of 2. But the ln of E to the RT is just RT. So R times T is equal to ln of 2, or T is equal to the ln of 2 divided by R. And here's a nice little table to tell you how long in years it's going to take to double the principal amount. I mean, to double the amount in your account compared to your principal based on different interest rates. So if you have an interest rate of 3% annually, then it's going to take you 23.1 years to double that amount. So if you put $50 in to an account that's collecting interest annually and continuously at a rate of 3%, then it's going to take you 23.1 years to have $100 of that. That's what this is telling us. Everybody cool with this? Awesome. In that case, that ends section 4.4. Before we jump into 4.5, let's go ahead and take a quick break. Come back in about 10 minutes. So come back at 7 o'clock.